Hey guys, welcome back to AlgoYogi. We are doing binary search series now, and our next problem in the list is arranging coins. So let's go to the problem on LeetCode and give it a read. Okay, you have n coins and you want to build a staircase with these coins. The staircase consists of k rows where ith row has exactly I coins. The last row of the staircase may be incomplete, all right? I mean, depending on how many coins you are left with, in the end when you are just building the last staircase. All right, so given the number n, which is an integer, which is basically the number of coins that are given to us, now we're going to build the staircases with these coins, and we need to return the number of complete rows of the staircase. All right, so really simple. Example 1, n is 5, that's the number of coins, and we started building like right over here. So first staircase basically takes 1 coin, second will be 1 plus 1, third will be 1 plus, basically 2 plus 1, so 3. So it's going to be like 1 2 3 until you ran out of the coins, and as the output we will return the number of complete staircases. So first is complete, second is complete, and you can see over here as well in the second example we are given the coins are 8. First staircase takes 1, and then second is 2 and 1 is 3, and then third one takes 3 plus 3 is 6. Last one, 8 minus 6 is basically 2 coins are remained with us, but that's not the complete staircase, so we'll just return the answer 3. So I think you can already think that this is going to be a really simple solution would be basically keeping a variable, let's say result. It's a brute force approach I'm mentioning here. So a result is initially 0, and then we will have a while loop that will say until n is less than or equal to, and let's have our current number. Basically initially, the current number will represent basically how many coins this current staircase is going to take. Result is basically how many complete staircases we have completed. Basically this is the number of coins that current staircase will take. So initially it will start with 1 because our current first staircase takes 1 coin. All right, second will take 2 coins. Okay, now let's come back to our algorithm, brute force algorithm I'm saying. So this has to be less than or equal to current, sorry, my bad, this needs to be greater than or equals to current, so that we can build this staircase, and then only we can enter inside this loop. And what we're going to do is basically reduce our n by basically current number of coins that's our current staircase will take, and then we can just increase our result by 1. Okay, by 1, rest plus equals to 1, and current will basically also be rest plus equals to 1. All right, and then we just finally come out of this loop, and we will return basically our results. So this will be our algorithm. So what we're really doing is we subtract the coins, current number of coins, from our total number of coins, and since we have built that case, we can increment our basically our result. But we also know that we need to increment our next number of coins that will be needed for our next staircase, and that we will check before entering this while loop. We will check beforehand as the base condition that do we even have enough number of coins to build the next staircase? If not, then just return the result. All right, this result I'm talking about. So now if you can see this solution, what's really happening, what must be happening is we have basically these coins from let's say 1, 2, 3 till n, and now we are trying to get to some number k that will be basically the number of staircases that we have built. This will not be n because initially it's starting with 1, then next staircase is 2, so you are already subtracting those coins from n. All right, that will lie definitely somewhere in between 1 and n, and this is the way we are finding it, and we are always subtracting the staircases that we have already built and the number of coins they have already used, so we are subtracting that. So the way we are basically moving in this algorithm is I'm talking about the time complexity here. So what's really happening is we are getting to this number k, and we are executing all of these steps, and let's just add them up. Let's just add them up. So that will be 1 plus 2 plus 3, and that will get to k. What is this number? So here we can use the formula k minus 1 by 2. I think that is how you find out the sum of let's check out if it is basically plus or minus. So sum of n nums, I mean easy searchable thing, so n plus 1, so not n minus 1. Let's come back. My bad. I mean these things you don't have to remind yourself. So this is our time complexity. This is the number of steps we will be performing to get to the k, and that will be k to the k square plus k by 2. Let's say this number is basically n, then 2n, and that will be basically you can just write it k square, this doesn't matter, you can ignore that. And then if you basically take under root both sides, then this will give you k equals to under root 2n, also under root n. That will be the time complexity for this brute force approach, right? And honestly it's not any better than n to the power just n, although it's definitely better, but in terms of how we studied in the in calculating the time complexity and space complexity, it would be just n to the power 1 by 2, and powers could just be ignored or something, and then you have this n. I guess no, I think they cannot be ignored, but under root 2n is still, it's bad. Can we do better? Yes we can, Mr. Perfect, Mr. White, we can do. How are we gonna do it? So this is what we were using, by the way. This is what we were doing in our algorithm, basically having this while loop and then trying to find out which. All right, so let's move to our optimized solution, which would be basically binary search. In order to find the same k, that will be, I'm gonna write down. So now you have already understood the problem, and it's just that k we are trying to find between 1 and n, where basically some of these, either we have built perfect k staircases, or k represents that perfect staircases, and there are some extra coins, but you can't build the next k plus 1 staircase, which will require k plus 1 number of coins, so we just leave it there. But the sum here, so k plus 1 by 2 would still be less than or equal to n. So this is a really important condition that we will keep checking in order to find k, and we're gonna find that k using binary search, and that will be basically having let me just move this little boy, oh my god, just right here somewhere, and then just delete this. All right, so binary search algorithm will start with left and right pointers, and we are trying to basically find this perfect k which will still hold this condition. This k will be basically, we find our mid, which is right plus left divided by 2, and this mid is what we are guessing. But what we really want to do is, we'll have this condition, basically what we have in binary search is that we are trying to find this high as higher k, where we had this condition still holding up for our middle. That would be our perfect k, right? A number lesser than that, that means let's just, let's move our left pointer ahead, and we will have this condition, while left is lesser than or equal to right. That means this will fail only when our left is greater than right. So right means that will be our best point, that will return this best k to us, because left will get greater, and we'll keep moving these pointers basically, appropriately closer to each other. So depending on the condition, and what conditions are those? Those conditions would be, we find this middle. So we find this middle number, oh my god, it looks so ugly. So we'll find this, I'm gonna get rid of this so that we can understand it better here. All right, I'm gonna get rid of, not this, so better to using iPad. Never mind. Okay, I'm gonna just write things down again. All right, so 1, then there is k, and then there is n. We have our left pointer pointing to 1, right pointer pointing here. Then we find our mid, left plus right divided by 2. Now this m we're gonna check. Basically, let's find out the sum until m, which will be m into m plus 1 divided by 2. This will give us this sum. Now check if this sum is greater. Check if this sum is where does this sum lie in terms of, when you compare it with, is it less than or equal to n? If this is, that means what? That means we could go a little higher. That means we could push our left to basically mid plus 1, right? And maybe there might be a case in the next loop, it might happen that next number is basically, when you find out that mid, then it might not hold up these conditions, but we would know in the next case. But like right now, we can choose to go a little higher, and later when you find out your next m, then we can choose if this ever gets basically bigger than our n, then we basically move our right pointer to mid minus 1. So I think this is like same as the problem that we solved like a few days ago, which was like inserting something at the right position, and it's just one of the pointers that you return, either left or right. And in this case, I think you will return r, and the reason is that when you have that while condition where L is less than or equal to R, this will we are only breaking out of this condition when L becomes greater than R. L becomes greater than R. even they're like they're true if they're equal and they enter the loop. What we really want to do is we want to return our R, and the reason is we want to stay safe in terms of where this condition must have, like, if this was equal to n, let's say if this was equal to n, then we will return middle. Yeah, otherwise we will check if this is greater than n. If this is greater than n, that means we need to bring down our right pointer to basically mid minus 1. Or if this was smaller than n, then we will basically be bringing our left pointer to middle plus 1. All right, so now I think we get what we are trying to say, and there will be basically two conditions. Actually, it's just one condition where this becomes false, which is like L becomes greater than R. So we just return R, our right pointer basically. I think now it's pretty clear, and this will be of binary search is basically you're bringing down your, I've explained it like a lot of times. This will be of log n time complexity. I'm not gonna go into the proving it again and again. All right, I don't know, I forgot to do it. But anyway, let's write down our solution. Okay, let's write down our solution. It would be a piece of cake. It should be a piece of cake at this point. Brute force solution, you can write it yourself. It was easy. We went through it in detail. So what I'll do is I'll have my left and right pointer pointing to basically 1 and n, while left is smaller than equal to right. Then I want to check my middle. Mid would be left plus right minus left divided by 2, and maybe to be safe, let's just close these. Right, okay, now let's find the sum. Sum would be mid into mid plus 1 divided by 2. Let's just divide it by 2. Now if s is equals to n, that means perfect. We found out the k, and that sum is just so equal to n that like we utilize all the coins perfect, and perfect k return our basically mid. Okay, L if s is greater than n, that means what? If it is greater than n, we gotta bring down our left pointer to basically mid minus 1. Else let's try to get a little higher. Maybe we guessed something lower than what it was supposed to be, so left can go higher, which is mid plus 1. Otherwise we come out of the loop and we return R, and we have explained in detail why we are returning R, since we are trying to get as big k as we can, and until this condition holds. Basically I didn't write that condition, which is basically s is smaller than n, and we return that, right? And this will only come out of this loop and left becomes greater than R. If it is greater than R, that could have been risky, which let's just return R, right? That would have worked perfect for us. All right, so now I'm gonna zoom out and let's try to run it on the test cases. Works here. Let's submit. Awesome, 100%. All right, time complexity will be big of log n, and then space complexity would be big of 1, which is constant. Back to AlgoYogi, marking it solved. See you guys later in the next problem. Until then, bye bye. You know what I'm saying.